There you are. Here I am, Season 10, Episode 3 of the Occasional Podcast, an interview with Mytek, or more elaborately known as What is the Future of Digital, Class D, GaN, and more. Mytek reveals all. A bit more dramatic that way, right? Well, we got kind of a lot to cover, and we have a nice, hefty interview that if you're a big fan of audio, digital audio, curious about Class D, curious about new technologies, where we are, where we're going. And even near the end of the interview, we talk about how our hearing truly works, things we can learn about evolution and the way we think about audio in terms of the way our head and brain translates it, not just our ears. It's a really interesting interview with the founder and designer from Mytek. But first, I want to mention we are off to Expona next week. If you're listening to this a little later in the week, we will be there. Check updates on the website, parttimeaudiophile.com. Facebook page will have a lot of new video content. And don't forget the YouTube channel. We will be giving room-to-room coverage from the YouTube channel, along with Facebook, and maybe a little bit on TikTok, but I don't know if you guys are on TikTok. Our data doesn't show that you are, but maybe you are. You can find us there too. If you are a ritual listener of the podcast, you will know that Mark Phillips and I, editor-in-chief at parttimeaudiophile.com, him and I have had this kind of little fun game we play at the audio shows. For those of you who have been to an audio show, one of the things that loves to be discussed is what songs get played there. Because even myself, when I first went, I was very surprised at the selection of songs. And ultimately what happens is there's a lot of songs that get played that aren't maybe the greatest songs in the world for most people. I know some people really, really love them, but they show off the systems, the rigs at the shows really well. But it's almost like a viral in real life sensation where almost everyone plays the same set of songs. And that set of songs ebbs and flows a little bit. It kind of changes. And one of the things we were trying to do is to expand that list just a little bit. And what Mark and I did was we would request our own songs at every room we went to and see if it kind of went from room to room in an interesting way. Did other people play the songs we like? Well, Chocolate Chip Trip, my friends, I'd like to announce, I feel like has officially entered that short list of songs that are worn out. It's an interesting little tune. I encourage you to test your system with it. But what I want, dear listeners, is for a little input from you guys. I am looking for a new song to play at Expona. I want it to go viral. I want it to get worn out. I was doing a little bit of Taylor Swift just to be controversial at the show, and it did not really work out. People didn't like to hear it. They didn't really love to have it played. There was actually a surprising amount of pushback, as if I was making fun of them. Not making fun. I just want a more diverse list of characters to be in on this play, right? So anyways, you guys let me know at theoccasionalpodcast@gmail.com what your favorite test track, stress track is that would make for a new listen at the audio show at Expona. I will listen to all the submissions and I will pick one and I will play it. And I'll let you guys know how it goes. But what I'm really looking for is a song that sounds fantastic. So it sounds great. The songwriting can be whatever, it can be good or mediocre. But it has to be outside of the box a little bit, outside of the tradition. So I'm looking for something unique, but great. Something appropriate for an audio show, but not necessarily one that you might hear. So we're looking to expand everyone's horizons with this exercise. So please send me your suggestions. I'll listen to them all. theoccasionalpodcast@gmail.com. And we will get this cooking. And maybe your song will become the new icon, the new worn out track that gets played all the time at audio shows. It's quite an honor. They make lists. There's plenty of stuff online for you to see. So that's my simple ask for you, friends. Now, as we say, on with the show. Here we go. An interview with Mytek. Almost everything you've ever wanted to know about digital, Class D, GaN, and the way to think about audio. Let's go. Our friends at ZMF Headphones are sponsors of today's episode. ZMF is a curated collection of various sounds and styles in the form of dynamic and planar magnetic wood headphones, designed by founder Zach Merbach since 2011. ZMF has garnered an A+ recommended component in Stereophile, Headphone of the Year on Headphonics.com, and been a 2-time winner of the SBAF Golden Schlong Award. ZMF headphones. That's the letter ZMF. Headphones.com. ZMF Headphones is the place to go to check out ZMF's collection and learn more. ZMF, traditional craft and modern acoustics. Today's episode is brought to you by Expona 2024. America's largest high-fidelity audio show takes place April 12th, 13th, and 14th at the Schaumburg Convention Center near Chicago, Illinois. Plan a trip to the Windy City this spring and discover over 190 listening rooms of high-end audio equipment and explore the latest in headphone hi-fi and Expona's ear gear experience. Tickets are available now at Expona.com. That's www.axpona.com. Everybody, thank you so much for joining us. I am here with the founder and designer from Mytek, but I'm going to let him say his name because I've already said it wrong twice. So can you please introduce yourself so I don't hurt your name?
Yes, hello, I'm Michal Jurewicz, designer and founder of Mytek.
Nice. Nicely done. So the reason I wanted to have him on the show, and we've discussed this in the past, is because there is an integration, you could say, of Class D topology that is coming for the high-end and hi-fi in general. And it is coming in many different forms, and we've seen it, and we've talked about it, but Mytek has breached that barrier and gone into some Class D designs themselves. And I'm going to let you talk a little bit about your approach, but I want to keep everybody in mind. We're at an audio show right now, and there are several product launches coming out with Class D being implemented into what would be traditional, maybe Class A, B brands that aren't known for this. So a lot of the tide, in a way, is shifting. Things are changing, but I think that it would be safe to say at this point there is a reluctance for change within the market. Usually, audiophiles are kind of entrenched in their ways. They like old school technologies. I mean, I think you would agree, tube technology is still around, and that's darn near archaic at this point. Vinyl records are part of the ethos. They're embedded into the culture of being hi-fi. So this change into Class D, I think online and a lot of the conversation around it is about a fear of change. So we want to kind of talk about that again, even though we talked about it last season. I think the update in this episode is really about what's going on now. And since this is a changing, evolving, emerging field for audiophiles like myself, I like to keep the updates coming. As the products come out, as we see more and more into the field, I like to talk about it because I think, in a way, this might be, and maybe you could throw your thoughts on this, this might be the future for a lot of people. I mean, do you feel that someday every amp in hi-fi might be a Class D, or maybe something else, obviously, but how do you kind of feel the future is for Class D?
Well, my belief is that, like any technology, Class D is going to get perfected to a point where it will be so good that it will be a prevalent technology. Of course, you're always going to have something else, but I think the dominant technology will be Class D. And you kind of already can see that in Pro Audio. A lot of amplifiers in Pro Audio, most of them are Class D. Most of active speakers have Class D amplifiers. It's definitely the future.
So let's talk about a little bit about your newest product. There's a monoblock that you've done. It's a little bit higher price point. The monoblock design in and of itself is, I feel like, inherently maybe high end. And it's clearly geared towards this crowd. How did you kind of look at Class D? how did you come to use Class D in this shape and form factor? What was your experience with it?
Mytek started playing with Class D designs about 6 years ago, when we basically designed the first small size Brooklyn amp that was basically meant to be an amplifier to accompany our DACs. We traditionally, actually for the last 30 years, made analog to digital and digital to analog converters. That were our core products. And we decided to venture into amplifier kind of field to just basically augment our and complement our audio chain. So basically wanted to have a full control from the Wi-Fi to the speaker about what we're doing with audio, and be able to kind of have a control over what we deliver to the speakers, not only through the DAC, but also through the amplifier. And when I started looking into what amplifier I would build, the choice of Class D was somewhat logical for us, in the sense that Class D circuits are very similar to DAC circuits. It's generally a loop that basically produces a square wave output in both cases, and problems and the solutions are similar for both. So whatever we learned from making good DACs, we could apply to basically design or improve the amplifier circuit. So we started with experimenting with existing designs. There is a number of particularly Scandinavian companies, but also things like Purify or basically a lot of companies making modules that you can just put in a box and basically have an amplifier. So we got a bunch of this, and we started experimenting with them. We hot rodded them. We did a bunch of things like changing the speed clock, changing the transistors to faster ones, changing the filters on the output, some parts inside as well, and generally try to figure out how much we can improve them to actually improve the sound quality. And historically, Class D had a pretty bad rep about sound quality. They were considered, especially when they came out in the early 2000s, to be very edgy and harsh sounding. You could generally describe that type of sound like if you were listening to 12-bit audio. And then maybe it got a little better, in 2010 maybe it sounded like 14-bit audio. And now maybe what you have now is maybe something that sounds like 16-bit audio. But basically that's the main problem of Class D amplifiers, is that because of what happens and how they work now, they generally end up losing the low-level resolution, and that's kind of what you hear. On top of that, the low-level resolution essentially gets masked by kind of an edgy and difficult to listen distortion. That's how you get the harsh top and all that. But they also have a very nice qualities. For example, they have very tight bass, and that always was true about Class D. And that results from the fact that you actually have very low output impedance, because you end up basically shorting the speaker to the power supply as you're switching the waveform. So they are very good with controlling the bass and accomplishing this. But the big problem is the precision and resolution on for the small signals. That's basically it was always a problem. And whereas you look at them, historically, they were improving like any technology starts, and then generally gets improved. And we are, I think, at a very interesting point now where there are some new technology, particularly new transistors called GaN FETs, that are able to push that whole idea further. And having said all this, I would say that, and maybe I will speak now about the waveform. So generally, if you understand engineering and if you understand the principle behind Class D, if Class D was perfectly implemented, in other words, if it produced the ideal square wave that had, ideal 90-degree angles, and if you were able to accomplish that, you will essentially have a zero distortion amplifier with absolutely straight transition curve that you don't need to correct with anything like, for example, negative feedback or on any type of correction, artificial corrections that you will have to do to correct for errors. So, generally the idea is that when the Class D amplifier, essentially it's a modulation. It's kind of, you can think of it like an FM station when you have basically a carrier frequency and then which gets modulated by the audio band essentially. So in case of the Class D amp, you have this carrier frequency of usually between 400 up to maybe a megahertz of basically very fast switching square wave that you then modulate, pulse width modulate to generally to accomplish the audio amplification. So the main problem with Class D amplifiers is not the idea. The idea is perfectly sound. Like I said, you will have zero distortion with a perfect waveform. But because the waveform gets distorted, that's what you hear. You hear those distortions that you can actually visually see on oscilloscope. Mm-hmm. You can see that instead of square wave, you're getting a trapezoidal wave that has basically overshoots and kind of all kinds of different things that don't look like square wave. Yeah. And all those things eventually make it to the speakers, and you hear them as basically the grounds that you heard on the typical Class D amplifier. Mm-hmm. And so the first thing that we did when we started kind of after, messing with all these modules that we had, we basically started understanding that part of the amplifier. And after we designed the Brooklyn amp, we designed a version called Amp Plus that essentially used faster transistor and faster clock to remove some of those distortion. And you can hear it between this older model and the newer model. The newer model basically sounds cleaner. Mm-hmm. But then we wanted, after we designed this very high-end streamer DAC called Empire, we wanted to design amplifiers that could go with this DAC that is extremely, extremely high resolution and extremely, extremely good sounding and musical. And we wanted this to be Class D. And we continued experimenting and trying to improve it, and basically felt at some point that we hit the wall and we couldn't improve it anymore. We could not accomplish with regular MOSFET transistors what we were getting with Class AB, or basically best Class AB amplifiers. Or typically when we do these design sessions, which I usually do with one or two other engineers, it's a lot of listening. We'll typically gather like 5 or 10 different amplifiers or modules or maybe other power supplies, and we actually have an A/B setup when we can switch between them and listen to them, and at the same time we often measure them, and sometimes we even record them. We used to actually record the output of the amplifiers using A to D converters just to be able to compare them later.
Later, yeah.
So we do this, all this stuff, try to kind of experiment and compare and draw conclusions and eventually move forward. And that's how we got to that point that we could not really improve this amplifier to compete with the best class AB. Huh. And then, we basically started looking at this GaN-FET technology and digging this. And there were some accomplished engineers that already done work before us on GaN-FET, and one of them that did a lot of serious engineering work was Skip Taylor, who designed several GaN-FET demo boards for different electronics companies and wrote some papers about this. And I talked to him, contacted and consulted him on this, and then eventually also talked to another engineer, Alberto Guerra, who has from HD Production, who also worked on that, and he worked actually for IRF, which was the company that made transistors, one of the companies that made transistors, GaN-FET transistors, and he had his own circuits, and we basically, after we tested those circuits or built our version, we had a revelation that this is it, this is the path forward. That basically, that technology allowed us to hear more of that detail. And the main, that very kind of simple test for that was basically listening to soundstage. We would play the sound through a regular amp, and we will have the Class D amp, let's say Brooklyn amp, and we'll have this size of soundstage, and then we switch to GaN-FET, and suddenly it expands. It goes several feet deeper, several feet wider. You basically suddenly start hearing things that weren't there, and the rest was basically just perfecting this initial discovery. Once we decided on GaN-FET and started tuning it, we understood it better. And basically now I'm absolutely convinced that this is the technology that we should pursue. And we built this empire monoblocks using GaN-FET transistors. And what is interesting, and one aspect that was the interesting aspect of the sound quality or the type of sound that these amplifiers produce was the experience with AGD production modules. Basically, when we started looking at GaN-FET, we are looking at Alberto website, and we're looking at this idea about the tube. He puts the output stage of the amplifier inside the tube, and I'm looking at this what the heck, It's a digital amp, and he says it sounds like tube. Yeah. How is that possible, right? Yeah. And then we do our listening tests, we A/B stuff, and we get to our kind of early, modified evaluation boards that are basically the early circuits of our GaN-FET circuit. And at some point, I'm having the same revelation sitting there in front of speakers, damn, this sounds like tubes, that. He's right. It has this tube-like quality. And I'm talking about this kind of velvety, smooth upper mid-range and top that is hard to get even with the AB transistors. Yeah. That's maybe the difference between Class AB and tube amps, that on tube amps, you always get this perfect kind of velvety, smooth top, and that's harder to get with any transistor amplifier, any Class AB amplifier. But the GaN-FET gave you kind of almost the same thing as tube. And that was a revelation, and that's something that we definitely didn't expect, but I think now understand, which basically has to do with the transfer characteristic of the amplifier. That is basically much more linear without feedback than it would be with class AB amp, when you generally dealing with an exponential curve of the transistor. So basically, now I would say one thing, that in terms of actual implementation, the technology is very difficult to work with.
Really?
You're talking about very short switching times of a lot of current. You basically want to switch 100 amps in a matter of 2-3 nanoseconds. And generally, we blew a lot of transistors, first of all. And secondly, just to kind of get this together and get the protection circuit working properly, and all the things that you typically will have in an amplifier like that is harder to implement because basically of the high speed of the circuits. Okay. You have to treat it a little bit like a microwave design, very short traces, So I would say that if you are a designer of a tube amp, that knowledge would be completely useless if you try to design the GaN FET, because you have to approach it different in terms of simply electronic circuit design. But the effect is very similar. You can get the GaN FET sound.
Do you think then, you're saying it sounds like tubes, but do you think you just used the word GaN-fed sound? Do you think that GaN-fed itself has a somewhat unique sound away from AB, away from A, away from tube? Does it have a unique characteristic to it when you get it right, inherent in the tech?
When I'm talking about the tube, I'm talking specifically about the high end, which it's not easy to do either with Class D, because you have that filter that limits your bandwidth at the output, right? So you can deal with the bandwidth that you're putting out by basically extending the sampling frequency, extending the bandwidth of the filter itself, but so you don't roll off the top, which can happen with some Class D amplifiers as well. But in terms of so I would say that GaN FET has the best of both worlds, in the sense that it has a very tight Class D transistor bottom end, when basically the diaphragm of the speaker is held very tight by low impedance of the transistor amplifier, or actually in the case of Class D, basically shorting it to the output, to the power supply, and that provides like very, very tight grip on the bass, and that's very, very good, and you can't get that with tubes, really. And then it has this beautiful tube-like top that you can get. So in that sense, GaN FET is kind of bringing the tubes and the best of tubes and best of Class AB together, if that's what you want to call the GaN FET sound.
I gotcha.
But so that's why I believe that because of that, this technology is particularly useful and future, and there is a lot of optimism about it for the future. But there is another element to it, which is basically cost and actual design requirements. The reason why GaN FET transistors were invented were exactly that they wanted to fix the waveform. But the square waveform used not for audio, but for power conversion, for solar, for wind turbines, for electric cars. They all use similar technology, where basically a PWM, pulse width modulated technology, is used to convert power from whatever the wind turbines producing to some useful voltage, right? And typically, because of the older MOSFET transistors, that you will get efficiency of about 85 to maybe maximum 90%. So imagine a 20 megawatt turbine, and you have, 10% of this dissipated in heat. There were huge boxes. And now if you can even bring it down to another 5 or 10%, and with GaNFET you can achieve something like 95% efficiency, suddenly your electronics for the car or this can be reduced in size tremendously. And that was basically what was driving this GaNFET, not the other word. We are too small.
Yeah.
So
no one cares about us.
So that's the driving technology behind it. So when you talk about this efficiency, that's another advantage of instead of these gigantic monoblocks that weigh 200 pounds and have multiple heat sinks and get very hot, you can now have a relatively small box with no heat sinks on transistors at all. Because with, let's say you have, maybe you need 100 watt, maybe 200 to power the system in your house. So if you have 95% efficiency, you may be dissipating, 3 watts or something. So you don't need all those heat sinks. So the whole thing can be smaller, and that's probably will have a big impact on a lot of applications going forward. So it's not only the sound quality, but it's also the way you implement it is advantageous. Yeah. So I'm a great believer in the technology, and so that's on the Class D technology in general. Now it is important to understand that, and this is one of the reasons why we went with Class D, we manufacturers of DACs. There is this concept of power DAC, okay? A circuit that it's like a DAC, but instead of outputting a line voltage, you output power, basically. So in other words, it's a kind of a circuit that combines a DAC and Class D amp together. And there are companies that already made this. For example, one of them, there is a box from Peachtree that has an amp that has a digital input and analog output, and it's a Class D amp with GaNFETs that basically takes a digital waveform, and instead of converting it to analog and then back from analog into Class D, it does a direct conversion from this original PCM to that PWM. And we are working on this as well. We actually have a pretty good circuit that does that, and that's probably yet another step into the future when you can basically kind of imagine a whole digital audio chain, and only at the very end you convert it to analog. And this is another very big challenge. It's very difficult to do properly. Actually, it's not maybe difficult to do in the sense of just accomplishing this, but it's very difficult to get it sound correctly. When you do this type of conversion, you essentially converting the magnitude and amplitude resolution that you have in a typical sample, PCM sample that is, let's say, 24-bit. You have this many, how many in 24-bit? In 16-bit is like 65,000, right, steps. In 24-bit is whatever times more. I forgot the number, but it's a very large number. Yeah. So you need, and PWM works by modulating the width of the pulse. So you have to translate that resolution that you have in amplitude to the resolution in the horizontal timeline. And that's extremely difficult to do because you're talking again the time precision of those pulses in the PWM output. and you again talking about precision of down to nanoseconds or maybe even less, and extreme accuracy that is very difficult to achieve by switching basically transistors. So that's the next frontier is to figure out how to do that conversion properly. Technics makes an amp that does it.
They call it a digital amp.
Right.
A digital amp.
Yeah, it has some chip that does that. There is a chipset designed by, I think, with help or somehow Skip Taylor was involved in that called D2 Audio, I believe, that does that as well. And there's a bunch of chips, but they all sound the way they sound. They could sound better. It is still not as good as the best D2A converter. So I think that the challenge is that now, who's going to come up with something that, when you do this type of conversion, the very weird things happen. You play music and it's just, all the frequencies are there. You hear the cymbals and bass but it's a completely it's very hard to describe, but it's like this unnatural sound that you just don't understand even, It's just this very kind of fake sounding effect that it's hard to comprehend if you are used to beautiful sound. And you can we actually had the early one, I did not mention Lingroff and the Tact Millennium. That was actually the first amplifier that used the technology. And we actually even had one for experiments here. And they have some understanding of that. They were trying to do that for 20 years, but they still did not really get there, in a way that I would consider, high-end, useful for the highest quality system. So this is still a challenge that somebody at some point will probably resolve. And then, you have these other approaches. Bruno Puzzi is an accomplished, he had the HiPex, he then had the Purify company, and they both very accomplished in Class D, but their approach is a little bit different. And I'm not sure what they actually think about GaN FET and if they're gonna try to implement it. My guess is that sooner or later they will. But for the moment, their approach was to increase the performance by applying traditional correction technologies, such as, for example, negative feedback. Which is a technology that you couldn't really, maybe you could in some kind of a specific digital way, but it's generally the approach that I mentioned about power DAC calls for something that has no feedback. Or maybe it has some digital feedback with some digital error correction. There is a chipset from a company in Netherlands that tries to do that. Correct the digital signal before it's converted to PWM. So in other words, there's a lot of things happening. It's not that it's just simply one Class D design. People are experimenting. People are trying to figure it out. You have probably about 10 companies experimenting with GaN FETs at the moment. We'll see, how we do. We'll see how they do, who's gonna. But generally, all the GaN FETs I heard were good.
Okay.
Yeah, it's, some were better than the other. Of course, the power supply, like always, is a factor in this. But totally, I'm willing to bet $500,000 today that in 10 years, if we talk 90% of amplifiers, or not, maybe 70 will be GaN FET,
Wow.
Or maybe 20 years. Let's give us 20 years, I think that's where this is really going. I mean, of course, it depends on the market and how people will accept it.
Today's episode of the Occasional Podcast is sponsored by Music Hall. For over 25 years, Music Hall has designed and built high-value, no-nonsense turntables. Audiophiles are told the more they spend, the better it gets, but Music Hall believes you can get great sound and build quality without breaking the bank. Their newest model, the Music Hall Stealth Direct Drive Turntable, was just awarded Part-Time Audiophiles 2023 Best Value Award. Editor Mark Phillips wrote, "It didn't take me long to realize a Music Hall Stealth turntable was a bit of a miracle. A great sounding direct drive table for a crazy low price." Music Hall remains a steadfast advocate for quality and affordability. Whether you're looking for your first or your last great turntable, do yourself a favor and visit musichallaudio.com to find your nearest authorized dealer or to order online with free shipping and a 30-day money-back guarantee. Today's episode is also brought to you by Woo Audio. The Woo Audio WA23 Luna headphone amplifier is engineered to deliver an impressive sound experience with an ingenious design that is not the typical audio gear black box. The amplifier is an all-tube, pure analog circuit, operating in Class A mode for a powerful, balanced sound, outstanding stereo separation, and a wide bandwidth across all frequencies, so you hear every note in the recording. No matter what music you enjoy, WA23 Luna delivers Woo Audio's commitment to a natural sound that is non-fatiguing for all-day listening. Learn more at wooaudio.com. That's WOOAUDIO.com, where better sound begins. Do you kind of feel like that GaN fed right now is very expensive because it's new and the price will eventually come down to bring it into these electronics?
No, it's always like this. When you design new technology, there is a high cost of R&D in the beginning. So you somehow want to recuperate that. So initially, whatever you invent, a new computer or a new amplifier, it has to cost more money if it's a new technology. But then you learn how to trickle down to a mass production product, and then it gets cheaper. And I would not, yes, transistors are more, GaN transistors at the moment cost probably, $6, $7, $8, $10, $15 each, while MOSFET you can buy for $1. Eventually, they probably come down to that. But transistors are not even the biggest cost of that. It's just simply just figuring it out and learning.
You're saying the raw hardware cost is more expensive, but right now the increased cost is a lot due to you have to design. You have to put so much into R&D to even get it out that you have to recoup
if you
all
simply
that.
replace, if you took an amplifier that, for example, it is a Class D amplifier, right? And you have regular MOSFET transistors, and you just replace those with GaN FET. First, you will have, it's not so easy because they're a little bit different.
It's not so easy, yeah.
No, in a sense that they need different drivers, but let's say you can work around that. Yeah. You will have to replace, for example, the protection circuits, because the GaN FETs are so fast that the protection circuit used in this traditional Class D will be too slow, and it wouldn't react, so you will blow the transistor. So you have to make it faster. So it's a redesign. You have to kind of redesign it and make it generally faster. And it's just initially it's always like that with any new technology. And of course, you also want to cash on the novelty and premium initially. So we made monoblocks that are $10,000 each. Of course, we could have started like Peachtree, who made this box for, I don't remember how much this amp is, $2,000 or $3,000. So it doesn't have to be 10,000 or 20. You can make it for less. So that's kind of. But again, Class D can be made sound really, really great. And to us, it's a great challenge, because I think in terms of Class AB, everything that you could possibly invent about Class D, I think it was Class AB was already invented. You know, that technology was out for 70 years. You had thousands, probably millions engineers trying to improve it. And I think it got improved as much as the regular transistor allows for. And I think venturing in this new territory of Class D is fun because it's kind of uncharted and it's more fun to invent and experiment, you know, maybe. So that's kind of what we said thinking. And of course, you know, that promise of the old digital audio path is also very, very interesting, you know, because I think my personal belief is that if you have proper digital signal path, and that means a lot of beats, you know, more than 24, probably 32, with something like a 64-bit processing and high sampling rates, probably, you know, 384 or even 768, which makes sense in terms of digital Class D. That if you use this type of resolution, you can very well challenge analog and make it more transparent and have more control on the sound if you use this type of resolution.
So, is there more transparency to be had? Is it possible that we can get more than we've ever had before with some type of evolution of technology, or do you think like it's just about cleaning the window at this point?
I think that that at some point digital can win with, like, and this is already happening a little bit in the pro audio. There was this phenomena of basically people using, if you understand the recording process, we can take, for example, a mastering process as an example, right? You want to master a record, you need to use an EQ, a compressor, maybe, you know, some kind of tube thing to sweeten it and so on, and you have like a bunch of analog things in a chain, right? So typically a mastering engineer would do would run the signal through the chain like this. It would be an expensive analog box, especially EQs, this and that, and it gets beautiful sound, right? And in early 2000s, you had this idea of digital audio plugin, which was basically kind of a replacement of an analog processing, let's say EQ or compressor, with some kind of what they called audio plugin in a computer that you could plug into the chain of digital audio signal, let's say in your digital audio workstation, and kind of get the same effect that you are getting with this box, you know, physical box. And I was skeptical of this in the beginning, you know, initially. You know, then when they came out, they just sounded, you know, it was kind of like trying to, a good parallel would be, for example, 3D animation. You know, you had
the uncanny valley, right?
Yeah, you kind of, you have real film when you have actors and real things, and now or for sometimes we're trying to replace some things with animation and make those things to look as good as the real thing, so we can't tell the difference, right? So where is that moment that you can't tell the difference, right? And you almost always can, you know, like this, you see those images generated by AI, or that's what I'm kind of talking about. You can't tell that it's not a photograph, it's an AI. So I thought in the beginning of those plugins that it's always going to be like this, that you basically cannot really properly simulate all this analog subtleties of, you know, to get same thing that we are getting with this analog gear. And then, you know, I remember this conversation. There is this engineer, George Massenburg, and actually I have some, relationship or contacts with McGill University that has some recording program. We did a lot of exchange of ideas with them. There was even like an MQA conference once with Bob, and there was all these engineers, Bob Ludwig, George Massenberg, and generally George Massenberg is a very good mixing engineer. He also understands a little bit of the plugins and electronics. He had some hand into doing designing EQs and things like that. But he's a very good mixer. He works. He did almost all the Linda Ronstadt, I think, work albums, and he was telling me then, and it was maybe like 2007. I don't remember that. He just mixes only in the box, meaning in the box means just the computer, no more console, no more outboard gear, just basically in the computer. I was like, but George, but how can you make it sound good? And I figured it out. I can make it sound good. And from that moment when he figured it out, of course, he had to change the methods a little bit, do it a little bit differently than it would was, but the results were very comparable to analog. And then going forward, it only got better. I did this paper at the AES show at some point where I basically kind of talk a little bit about the subject of resolution. And a lot of this had to do with the computers going from 32-bit to 64. When you had a 32-bit system, your signal path was essentially 24-bit. So when you went to a plugin, you went with 24-bit. It did some computation, and the result was, let's say, 100-bit, because that's the nature of digital signal processing. You get more bits on the output than you get on the input. So because the system was only 32-bit, it gets rounded to 32-bit float, right? And you basically throw out the 70 lower bits that contain some information, but you just throw them out because you cannot really get them forward because the system is limiting you. So there was this big change at some point where you went from 32-bit systems to 64-bit. And 64-bit, suddenly, if you think about the amount, 32-bit is 24-bit and 8-bit of Mantissa, right? And then 64-bit is, I believe, 53 and 11, right? So so you suddenly have, instead of 24-bit signal, you have 53-bit signal. And 24-bit times 6 gives you a dynamic range of, And here you have basically much, much higher dynamic range, another twice as much of dynamic range. So that means that this whole the lowest, finest resolution still gets preserved and transported farther in the chain. You don't lose it. So that's what I mean by, preserving the highest number of bits and high sampling rates, because that large is just like a large road. The more things fit on it, and you don't lose anything when you go forward. So this happened with digital signal processing in the pro audio world. As this happened, the plugins got better. Mostly because of just simply increasing resolution. But then people started using higher sample rates. At some point, 96K became a standard for production because it was that hard drives were cheap and you could just do that. And basically, this whole thing resulted in improvement, in a great improvement of sound quality, of digital sound quality. When you compare digital sound quality of today, on average, is way, way better than it was 20 years ago, on average. I mean, I'm saying on average because there were always exceptions, but on average, absolutely. So I think that with audiophile audio chain, kind of you can expect similar thing happen. You know, that if you can keep that digital in this high resolution and properly put it through the chain and output it, you will achieve a more transparent sound than you would do that through running through a bunch of several stages of analog equipment, because analog equipment, no matter how great it sounds, it always loses a little bit of information. There is always some loss of resolution when you run it through any piece of analog equipment. And it doesn't have to, it's just the nature of analog. It's just there is noise floor.
Noise floor.
There are different. There are distortion. There are limits in bandwidth. It's just
the aggregation of distortion, noise floor, all of these.
It's again, an example is photography, for example. You know, you can get bigger film, you can get bigger size of a frame, but you always have a problem of the analog noise of the
film
actual
grain
film.
size. Yeah, film grain.
So it's similar to that. You know, when you imagine that you made multiple Xeroxes or something like that of something.
Yeah. So anyway, every chain, every piece of the chain adds to almost like copying a photo over and over again. It loses resolution.
And that was actually what Sony initially sold as this perfect digital sound, because that's what they meant. That the digital sound is perfect.
The reason I laugh is because it's such an infamous line now. We look back on it saying the perfect sound, and it wasn't really clearly explained. It was definitely marketing speak, but like we look back on it now and say this perfect sound, or the promise. Okay, it's the promise of perfect sound faltered greatly. It was not delivering on what they said it was. But from what you're saying, I think you just clarified what exactly they meant or thought they wanted to push at the time.
They meant the fact that you make one copy and then that copy can be indefinitely copied over and over and doesn't deteriorate.
Is that true in your mind in digital?
Yeah, if you do it properly.
Okay.
There are all aspects of that, you know, there is the way you transmit it, there is a jitter, a clock jitter issue, there are all those things. But generally, we know how to transmit data without losing a bit.
That is 100% true. Then where do you land on the... So there is some debate about that with cables. Like when it comes to a digital cable, an audiophile cable, without getting yourself in too much trouble, is there any truth that a better...
No, of course it's true, but digital cables have to do with jitter. And it doesn't really have to do with the information in form of the bits or how many bits of which one is 1 or 0, but more like how they are transmitted in time and when they are read, and that's what I could do a lecture about jitter, but you have plenty of them on there. So yeah, it's absolutely true that the quality of digital signal, and that includes everything, you know, computer software to a certain extent, you know, when you think about how is, you know, like we all experience now that some software sounds better than the other. You know, you play the same music from this player and it sounds different than you play it from another one, right? And they claim to be both perfect, right? So very few people go through a challenge of testing it. But the first thing that occurs to me often is that the programmer makes a mistake.
Right. That is a really good point.
There is no way of really knowing what they wrote if you don't know. So the only thing that you could, for example, if somebody is claiming that something is beat perfect, you better test it. It's not a trivial test. You have to put the number on one end and get the same number on the other end. We can't do it with sound.
And I just want to point out too that this element of program you say, it occurs at many steps along the line. It's not just at the playback device line, right? There's, correct me if I'm wrong, but there's programming that is involved at the DAC level. I'm assuming you maybe you could jump in here and say there's programming at so many points that if there is it's not that it's inherently making it better or worse, but if there is a programming issue, it can degrade this perfectness that we kind of are talking about from one stage to another. But the point I'd like to make is that it's not just at the playback, because there was so much online fodder about playback software. How could playback software make any difference? It's just ones and zeros. But what you're saying here, in essence, that not only is it the playback software, but the DAC programming and this and that, if you make a mistake, degradation could occur.
It's I work in a recording studio, and I saw what happens with tapes and masters, and anything can happen, Often record companies have no even idea what they've got on the shelf. They don't know if the tape is a copy or original. They usually, if properly done, they usually were well marked, on the tape itself. But in terms of the actual knowledge of what was done on a particular session, what tapes were recorded in 1970 by whoever, and came out from that studio, you often don't know what happened. You often don't even know what is original. So with record companies, what we had, for example, we sometimes, and I don't have an exact example, I don't remember the titles, but I wrote some down before. You play something from, streaming services, be it Tidal or what have you, and it reads 17-bit or 23-bit 96K or 17-bit. And people ask me, why is that's wrong, right? Because our DAC can actually measure how many real bits it gets. Mm-hmm. It's very simple. You simply see how many zeros you have at the end, and that you determine how many active bits you have. And some recordings on a server have 17 bits, or they have 23 or 22, and they should have 24, but they have 23. Somebody made a mistake somewhere. And basically, they didn't even realize it. It went through the QC somehow, and then it ended up on the server. And this is happening all the time. Yeah. So you can't get things for granted that they are exactly the way they should be if you don't know the whole process, that what happened with the file before, how it was done. So that, but, having said all that, again, more bits and higher sampling rates helps you, because you just basically have more bits, you can lose more,
So are you in essence kind of saying, maybe in a way, that the reason analog differed from digital was that we just kind of had a bandwidth issue? You're saying all this resolution, the plugins, these things, is we just didn't have tech in place when we first set out to do digital. Because I think one of the things we talk about on the podcast a lot is how really audio took a step back when it first leapt into digital. We were like we talked about earlier, we were promised perfection, and we got something less than that. And audiophiles have been reluctant. This is part of the reluctance for maybe Class D or digital to these guys, is that when it was first introduced, the D to A converters were just not up to speed.
Well, there is another element of that, though. Yes, this is all true that early digital, imperfect digital, had a role, but. I want to mention just the general nature of digital. Pulse, PCM stands for pulse code modulation. It's a modulation. What this really means is that when you do different processes, digital processes, going through digital filter or do something with the signal, you can end up with artifacts that are not harmonics of the music. Okay? For example, aliasing is an effect like that. The digital filter artifacts can be like that. You generally produce artifacts, or you could say distortion, that are not related to music. They basically are like the difference between the musical frequency and the sampling frequency, and kind of folded down. So you end up with basically our ear, and I'm very much, a scientist, and I believe in generally evolutionary approach to things and evolutionary psychology, and also I believe that our ears are product of evolution that actually happen in the analog world. And analog world generally does not have these things, doesn't have this type of artifacts. We only, if you make sounds of instruments, they are usually harmonics. You have a bass frequency, and then you have the second, third, and harmonics, and they have different loudness depending on what type of instrument. You have more odd harmonics if it sounds sharper. You have more of a even harmonics if it's a wood instrument. But generally, that's kind of what our ears, and not even our ears, we should be talking about our brain.
Right.
Because our brain is really kind of an amazing, when you think about it, an amazing machine. You have a waveform that looks basically like a waveform that gets into our ear, and our brain takes it, and suddenly we have a sound stage with guitar here, drums here. And how does this all happen? It's basically the processing of our brain. So I think when the brain gets those artifacts that are produced by digital, those basically non-harmonic distortion, it doesn't know what to do with it. There is this effect, for example, of a steep FIR filter that has an element called pre-echo. So you have basically, if you run a pulse through it, you will first have a small echo that would be maybe at like down to 100 dBs. Then you have the actual pulse, and then you have another echo. So you're listening to this, and you can hear that it sounds absolutely unnatural and weird. You have an echo signal and an echo. It doesn't exist in nature, but the digital signal produces that, and our brain doesn't know what to do with it, and basically doesn't like it. We just kind of like, this is annoying. There's something wrong there, right? So that's part of the digital as well.
Is there some reason why analog, maybe like you were saying, harmonic, and some might argue the distortion of tubes, it somehow sidesteps that in some way better?
First of all, just taking on this digital filter example, the reason why DSD sounds so good the way it does, because it has no digital filters. So actually, a lot of people describe DSD as sounding analog. They call it the best digital that sounds like analog. And it's true. I totally agree with that. And it is because it doesn't have digital filters. That's the only explanation, because we don't understand exactly how it works. So when you say about analog being analog, people run analog, run harsh digital through analog, but that's a little different. I'm not sure if that's what you're asking, because if you run, harsh digital signal that has a lot of, upper harmonics, or like just basically annoying kind of high frequency artifacts, they will just get filtered out. That's basically what the analog does. So you run it through some tube equipment, it goes through a transformer has limited bandwidth, filters it out, some other things get filtered out, it's smoothed out at the output. That's basically what it is. But the basic difference between analog and digital is still remains the same, that analog is completely natural for us, for our species, and digital is not.
Okay.
And now you can kind of imagine what happens if, Meta puts us in all this, in virtual reality universe where everything is digital. How are we gonna like that, when it's not perfect? I'm actually very skeptical of that. But I think that with sound we understand this enough now to know that we can kind of minimize these artifacts to a point that they are manageable, that they are not annoying. Plus, what we can also do, we can create digitally, for example, examples are plugins. There is plugins there is, for example, vintage warmer plugin made by my friends in Warsaw, a company that makes audio plugins, PSP, is basically emulating tube sound, or like not really tube sound, but actually particular sound of some particular device that just basically sounded good to engineer, and now they basically emulate it digitally, and you can use it and just kind of get that, that type of. So I would say that when you're talking about future digital and what you could do with it, we're not really only talking about the transparency and being able to preserve the signal from the input to the output, but also that we can emulate the analog processes if we want to, but we don't have to, It's a little bit like, when you think about the sound from certain era, and when you think about recordings done on 78, and then, how that sound changes. Sometimes you even want to do something like this just to get a certain effect and feel about your recording. Recording doesn't have to be an exact copy of reality. Sometimes people experiment and do interesting things to make it sound, So
I think I talk about that envelope filter on the snare from the 80s that was so popular. That was not close to reality. It was like a whang, whang, and you hear it, and I think of the 80s, but exactly like you said, they did it because they wanted to try something different. It wasn't an exact copy of reality, but now in hindsight, I feel like maybe it was a mistake.
Some things, become classic, some get forgotten, But having said all this, also, when you look at photography, you kind of see a similar trends, right? Like the first digital cameras were really crappy. Then now it got so good that you couldn't do anything. And I think we are at this point with digital as well. But I think it's very important to, again, maintain the resolution, maintain the high sampling rates that helps you deal with filters, because essentially when I mentioned this DSD example versus PCM, the impact of the filter is directly proportional to the sampling frequency. If you sample at 44.1, you will hear filters much more than if you are at 192. That's the whole point of 192. It's not only to increase the bandwidth to 100 kilohertz, which also helps a little bit, but it's mostly to just move the filters away, so they are basically not impacting the audio band as much, So as you increase the sample rate and the amount of bits in PCM, in fact, in terms of the actual perception of what you're hearing, you're getting closer and closer to DSD. And I think, once you go like 768 and 32-bit, it's very, very hard to distinguish it from DSD. So that's kind of, I think, where the things are going for practicality. We will stay with PCM, but there will be a lot more digital signal processing of different things. And now my personal thing here is that, again, like with anything digital, once you can do all this processing, the question is, what are you going to do? And some people will do crazy thing and totally mess it up. And some people will just do a very gentle things, a measure that will just do good things but not bad things. So you know, we have all those options, but you will have them, and I think that's generally the future of digital. So yes, vinyl will stay here because people, you know, my 16-year-old daughter likes physical things because they have too much of a virtual. So they like physical. So because of that, the vinyl will probably stay. But the rest that leads to production of it will probably be digital.
Yeah.
You know, it's very hard today there are some people still using tape and this and that, but it's more of a kind of experimental hobby than a kind of
Who even shoots on film cameras anymore? There's only like a couple of labs that'll do it, and there's only very few people producing the film anymore. Yeah. And give that another 20, 30 years.
The same problem you have with recording tapes. They used to be made by a reputable large companies like BASF or 3M or Ampex. They don't exist anymore. They don't produce them. And it's a complicated chemical process. You have to put all this thing on this thin film and produce the tape. So now there were people in California trying to do tape. And basically the tape they can't do this as well as that or old tapes were made. So so there are all these things, yes. And
that's too bad. I mean,
Mm-hmm. But that's kind of, you know, on this topic of future of digital.
Yeah.
Yeah, and it all connects with Class D.
Well, you seem very optimistic about it. Let's just bring it back to making money. There are a bunch of ways to make money in this industry, but it seems like the mantle that you've put on yourself is to kind of develop and create something new, push the envelope forward. Because I'm pretty sure you seem like a smart guy. There might be ways for you to kind of like sit back, create a product cycle like Apple does with their phones, where we don't see much improvement anymore, but we do these other things to try to spurn sales. You kind of seem like you are, and it's not every manufacturer, but there are a few out there that see this like you do, where they're like, what is it about it that calls to you that you need to like do this instead of doing because this seems hard, but creative. You could probably choose a path that's easier, but also still makes money. Why are you doing all this?
I think you asking me about the career choice between a scientist and a Wall Street broke.
Yeah, Wall Street broke.
Okay, my parents were scientists. I have that curiosity. I don't know if it's in my genes or I learn it, but I do have curiosity about learning about new things, and a lot of people who design equipment do. Yeah. They get kick out of finding and discovering new things. Yeah. So when of course everything can be perfected and we can make a wheel more round and things like that. When you venture to this like complete new territory, when there is still some uncharted, that's like really exciting. I get kick off from that, You just basically kind of suddenly have this ideas what this can be and experiment. And I mostly do it because of just that simple curiosity. And, I would describe myself more as an inventor or a person that can design a product that will sell than a good businessman. I don't think I'm doing the business by necessity more than a choice. And I would very much want help with that if I could just focus on R&D and inventing new products, because that's my creativity. And it's generally when you work with group of mindful engineers, there's always this brainstorming and this and that. It's fun. That's why we do it. It's, I guess if we try to make a lot of money, we'll have to be in some other industry.
Yeah. That's exactly right. That's the point, that people don't come into this very specific industry to make a lot of money. There are a large group of passionate individuals who are here because they want to be here. Yeah. And they want to be here not just because of the music. Because I think that's why people listen, is because of the music initially. Yeah. But you're talking about something a little different. You're talking about creation, inspiration, pushing the envelope forward, pushing technology forward on a new landscape that is surprisingly still uncharted after this conversation we've just had. I'm just kind of pleasantly surprised how much we haven't gotten there with audio, how there might still be, as I said before, more resolution to be had. Or maybe if it's not in resolution, because from my experience with listening, and it's incessantly all kinds of stuff, that there has got to be there might be room to grow, let me just say, with both a sense of resolution and detail, but also naturalness. Because what you spoke about too is that with digital, at least, you can get like this sense of resolution, but the harsh top and all those things you describe, it doesn't sound like I'm outdoors. You know what I mean? You can immediately tell the difference between a real bird and this recreation. So like those elements, those unknowns of how our brain fully decodes things, is where the growth, I think, is in a way.
Well, it's getting there in terms of birds and soundscapes. It's getting there, Like I remember an episode when I was like early into recording. I was maybe I had this I had some heroes in my career, and one of them was a gentleman from Poland that was basically kind of an engineer, but also recording engineer, but inventor as well. Władysław Wygnański. And and I remember an episode with him. He needed a soundtrack of frogs. And we were with my parents. I maybe was 12 or 13 in a vacation home that had a big lawn, and there were a lot of frogs at night. Mm-hmm. So he comes with his Nagra one night, and we are like, and we are kind of, trying to get with two microphones and this Nagra close to frogs and record those frogs. And that was beautiful, there was this kind of chorus of frogs that we recorded. Then they used it for some theater piece, and so that was the nature sounds. I didn't really do much of it later, although I worked with some engineers who did samples, 3D samples in particular for Hollywood movies and stuff. So you have all these technologies that are eventually commercialized and maybe are not as good as they could have been, although there's still kind of hoping that they can be. And I think that I was actually a few times recently in some theaters when I noticed that the sound got improved from the past. I don't know if you've noticed that, but the Atmos system from Dolby actually produces better experience in the cinema than anything before. And it's because the way it works and all that. And what was the movie? It was the Poor Things. I saw it in relatively new cinema in Williamsburg in Brooklyn. And I was kind of listening to the sound. I was like, damn, they did a pretty good job. It was just kind of like a high resolution, high quality recording. And prior to that, also I heard the latest Star Wars. It was like 3 years ago or 4 years ago in one theater, and that was basically in an orchestra. John Williams, of course, but the orchestra recording sounded really good. Like it was a very good audiophile system, but we were in a theater. So it does. Here and there it gets better. It's not everywhere, but yeah.
I think one of the things that never ceases to amaze me, at least living in Los Angeles, is the sound system in the theaters. I'm amazed by the dynamics. They did it right in some theaters. I'm like, I can't believe how good the dynamics are in this large scale system. I feel like I'm right back here at an audio show sometimes, and it usually catches me most when the music comes on, and I can really get a sense of what I'm used to hearing it like, and I'm like, wow. But that's Los Angeles. They dump a lot of money into the theaters here. They make a lot of money, so I'm sure that not everybody gets that. The theaters I grew up in at home, maybe it was a long time ago, or the size of the theater, garbage, flat, everything. But out here in LA, it's been good.
Yeah, this theater in Williamsburg is relatively new, maybe 3 years old or something, maybe more. But I think that's part of it. It's a new equipment and everything is brand new, and it was better. Yeah. So I don't know, but I think they're all. Like sound is this very kind of subjective medium. It's invisible. You can't touch it. It's just like, and it is very prone to subjective interpretation. So I think there will always be people experimenting it and always fascinated by it, and there will be more and more ideas with sound. I'm pretty sure. You know, this whole ambisonic implementation that you have in Atmos and 360 and the Sony's 360 and all that, and that's also Edgar Chouery, who does that in Princeton. I'm not sure if you know this Bach system, you know, the stereo thing that he does that becomes 3D. All those technologies, if properly done, they produce very convincing results. And I'm pretty sure that we still have a lot of work that ahead to kind of improve and make the sound kind of easier to mold and more natural, because up until now, or even, you know, here in this kind of in our kind of sphere of audiophiles, a lot of it is done a little bit kind of like trial and error and blindly. You know, it's like, oh, let's try this cable, let's move speaker farther, closer, this and that. It's rarely very kind of scientific unless you get the person who really understands that. So that's because of the basically nature of it. If we saw the waveforms in the room, it would be easier to set up speakers. Well, we don't see them. Yeah. So I think that there is still you know, a lot of room to experiment, and it will be digital. It will be digital, but if you know what you're doing and you're not overdoing it, yeah.
Do you think that at some point we will reach some type of plateau where there's nothing more to pull out of sound quality? We will reach a technological plateau where we say it's done, because it was kind of promised that the CD, if you remember, they're like, this is as much as you need. But then later, I think there's an argument that maybe it wasn't.
I think that the oversimplification with CD results from oversimplification of our understanding how our hearing works. We, you know, basically you had this, okay, you can hear to 16 kilohertz, this guy can hear till 18, oh, this guy is brilliant, can hear till 20. And then maybe you can hear it down. You know, you have a hearing range of 120 dB or something like that, and that's basically where assumption that's you know, that's kind of a sensor our ear, but there was absolutely no understanding at that time of how our brain works. And an example could be that, okay, what sounds better, CD or analog tape, master tape from analog studio? What do you think should sound better? Typical answer is the analog tape is the holy grail, right?
Yeah.
And it is. You know, in subjective terms, it sounds better than CD. Yeah. But CD has a 96 dB dynamic range, and how many dB on the tape?
Is it less?
60. You have 60 dB signal to noise on an analog master tape in a recording studio. So what happens is that you have this tape noise, but you have signal going into the noise. And our brain is capable of basically distinguishing that signal from the noise and picking it up just down to 30, 40, 60 dB down into that noise, and we still hear things that are buried in that noise. But that assumption did not exist then. They thought that, okay, we do CD with more dynamic range, measurable dynamic range than the tape, and it will be better. And it turned out the other way. Because the brain, then there is this kind of talk about, our Neanderthal ancestors were sitting next to a waterfall and they had to hear, the predator approaching them even with all this noise of that waterfall, and they had to get those, danger signal out of the general noise, and that's how our brain figured it out, So once you start learning about how brain works, you can learn much more how we actually, what happens with the sound. And there is a lot of science now about this that did not exist 20 years ago. A lot of it, there is a book about, there's a Canadian author, I forgot his name, My Brain on Music, My Brain, or Your Brain on Music. There is a number of publications that talk about that when you basically go into MRI scanner and they play Mozart for you and they test what happens, right? And for example, is Mozart effect true? That you listen to Mozart and you get better in math or stuff like that. That's called Mozart effect. I'm not sure if you're familiar. So there are all these things that we are discovering now about the brain that will explain a lot about what we do with sound, that will help us to design equipment better because we know that, So that's what's also going to happen, and like with brain, I think it is a little bit like the more we know, the more we realize how little we know, right? So but it's important to keep that in perspective to kind of.
So there's this old adage or whatever. It's like, you measure something and it sounds bad, but it measures good. It means it's because you didn't measure the thing that's making it sound bad. Do you think that's somewhat true, that there's some elements of stuff that we don't understand about the brain, but if we couldn't measure it, then we get the perfect sound and everybody's going to be happy with the perfect sound?
When somebody tells you signal to noise, dynamic range, those are all useful general measurements, right? But it is a little bit, like somebody telling you that you're renting a hotel room that is this size, but that's all the information you have. Right. And it's kind of, you need to know more, really. So that's, I think it's in that effect, you know. Now, if you're talking about things that measure bad but sound good, we are again going back to this analog effect where analog signal. And okay, if you take, for example, a violin, right? A violin is strings making sound, but then you have a wooden box that adds this whole reverberation and harmonics to the strings that actually make the sound beautiful. So you can take a sound and do something with it and make it more beautiful, change it in the analog world, right? And the same thing you can do with a piece of equipment. You run through some tube amp or what have you, and it's suddenly kind of more like whatever you want it to be. Like some people like, just this very kind of relaxed jazzy sound, and some people like this or whatever. And you can kind of, by basically running the signal and getting harmonics and distortions of a certain way, you can kind of get the distortion to be pleasurable. We actually, in our DAC, in this newest DAC, in either Empire or the Brooklyn Bridge 2, we actually introduced that function into the DAC. We have now an option when we can control the amount of harmonics that comes from the DAC. And it was basically something that was an experiment that turned out into a future of the converter. We have a button that you can, it's not a digital effect. It's done in by manipulating the output stage of the DAC, changing the parameters of the state of that stage. And basically, what we used to design DACs were for minimum distortion, and they sound clean and nice with minimum distortion. We call this sound normal. And then we started messing with adding like the second and fourth harmonic to see what happens.
Adding distortion.
Yeah, distortion. And it turns out that as we add second harmonic, sound stage stays the same. Resolution also the same unless you add too much of it. And but everything becomes more groovy. So you kind of feel it's more musical.
Thank you so much for coming on the show. I appreciate all of your insight.
Okay, my pleasure, and thank you.
The Occasional Podcast is a production of the Part-Time Audiophile Network, which includes parttimeaudiophile.com, The Occasional Magazine, the PTA newsletter, and audiohead.com. You can stay in touch with us on Twitter, Facebook, Instagram, and YouTube. The Occasional Podcast is produced and hosted by Brian Hunter, executive produced by Scott Hall at PTA Productions. The Occasional Podcast and its original associated music is monitored, mixed, and mastered on the Focal Trio 6 BE studio monitors. If you haven't already, please subscribe to The Occasional Podcast on iTunes, Google, Spotify, or wherever your favorite podcasts are downloaded.